Now we'll add our solution file, named 0006-zigzag-conversion.py. Let's open the file and start building the solution step by step. Let's start by noting the complexity and that we don't need any imports for this approach. We process each character once, so runtime is linear in the length of the string. Now we'll define the solution class, which will contain our convert method. All LeetCode Python solutions typically wrap methods inside a solution class. Next, we add the convert method signature with type hints and a short docstring. The method takes the string s and the number of rows and returns the converted string. Let's handle the trivial case. With one row, the zigzag is just the original string. When there's only one row, there's no up-down movement. We can return immediately. Now we'll add our state. Rows collects the characters per row, backward tracks direction, and I is the current row index. We build a list of strings, one per row, to accumulate the zigzag pattern. Now we'll loop through each character appended to the current row and check if we're at a boundary row. Whenever we hit the top or bottom row, we should flip the direction of movement. We toggle the direction at the edges. If moving backward, we go up one row by decrementing I. The backward flag encodes whether we're going up the zigzag, backward, or down. Otherwise, we move downward by incrementing I. The loop continues until all characters are positioned. Together, these steps simulate the zigzag traversal across rows. Finally, we join the collected rows to produce the converted string. Reading row by row reconstructs the zigzag output in the required order. Let's test with 3 rows. The expected output is PHNAPLSIGYR. This is the classic example from the problem statement with 3 rows. Now try 4 rows to see the zigzag path change. With 4 rows, the down-up cadence is different and produces a different string. Finally, test the single row edge case, which should return the input as is. Great job! We handled edges, track direction, and built the output efficiently. Now let's add the Python file where we'll implement and explain the reverse integer solution. I'll open the file so we can build the solution step by step. Let's start by noting we don't need any imports and documenting the time and space complexity. These comments set expectations and clarify that our approach is constant time and space for fixed-width integers. Now we'll add the solution class that LeetCode will instantiate. LeetCode calls methods on this solution class, so we place our logic inside it. We'll declare the reverse method that accepts an integer and returns its reverse form with overflow handling. This is the required method signature. It takes x and returns the reversed integer. Next, convert x to a string for easy slicing and initialize a placeholder for the answer. We start ANS at 0 and later replace it with the reverse value as text before converting back to int. Before processing, add a guard for inputs already outside the 32-bit signed integer range. If x is out of bounds to begin with, we immediately return 0 per the problem specification. Handle the positive case by reversing the string with slicing. The slice ::-1 efficiently reverses the string representation of a number. For negatives, strip the minus sign, reverse the remaining digits, then reattach the dash prefix. Again, ::-1 reverses the digits while we manage the sign manually. After forming ANS, verify the reversed value stays within the 32-bit signed range. This post check ensures we comply with the overflow rule by returning 0 if out of bounds. Finally, convert the reverse string to an integer and return it. The int conversion also removes any leading zeros from the reverse value. Let's add a quick test to run the method and observe the result. This should print -321 since leading zeros are dropped when converting back to an integer. Let's create the solution file where we'll implement my atwa. We'll open the file and start coding step by step. Let's start by adding a brief header. This solution uses only built-in parsing, so we don't need any imports. No extra libraries are necessary. We'll parse the string manually and handle bounds ourselves. Now we'll add the solution class that LeetCode expects to instantiate. The solution class is the required container for our myAtwa method. Next, we'll define myAtwa with a docstring summarizing steps. myAtwa takes the input string s and returns the parsed 32-bit signed integer. Let's initialize variables x for an optional sign, y to accumulate digits, start for the first non-space index, and nums for quick digit checks. Using a digit string lets us do constant time membership checks like C and nums. First, we skip any leading spaces. The moment we find a non-space, we record its position and stop. This check finds where the real number begins and avoids leading white space. Now we scan from the first meaningful character. If we encounter a sign and have not read any sign or digit yet, we record it. This allows exactly one leading plus or dash before any digits are read. If a second sign appears, we stop. Otherwise, if we see a digit, we append it to y to build the numeric part. Digits are accumulated contiguously. Once non-digit appears later, we'll stop parsing. Any other character ends the scan because the valid integer prefix has finished. If we did not collect any digits at all, we return 0 per the specification. No digits means no valid number prefix. The answer is 0. When the sign is negative, we convert y and clamp below dash 2 asterisk asterisk 31. If the magnitude exceeds 2 asterisk asterisk 31, we return the lower bound. This branch enforces the lower limit of the 32-bit signed integer range. Otherwise, treat it as non-negative. If it exceeds 2 asterisk asterisk 31-1, clamp to that maximum. Otherwise, return the parsed value. This condition enforces the upper limit for 32-bit signed integers. Finally, let's add a small test harness to run a couple of typical cases. We instantiate solution and print results for inputs with leading spaces and mixed digits with words. Next, let's add the main Python file, where we'll build the solution step by step. Opening the file so we can begin coding. Let's start by noting the naive recursive complexity and importing _cache, which we'll use later to speed up the recursive DP. _cache will let us memoize function results to avoid recomputation. Now we'll add a first purely recursive solution. If the pattern is empty, the only match is an empty text. Then we compute first match to check if the first characters align or the pattern starts with a dot. First match captures whether the current characters match, which drives the next decision. If the next pattern char is a star, we have two choices: skip the X asterisk or use one match and stay on the star. Otherwise, consume one char from both text and pattern. This condition handles the special star behavior that creates branching in the recursion. That exponential solution can time out, so let's implement a top-down DP with memoization that runs in OTP. We'll improve both time and space by caching overlapping subproblems. We define a memoized helper DP, TIDX, PIDX. If we've consumed the entire pattern, it's a match only if we've also consumed the entire text. DP tracks pointers into text and pattern, representing the subproblem text, TIDX versus pattern, PIDX. Otherwise, compute first match and check if the next pattern character is a star, which gives us a choice similar to the naive solution. This mirrors the character match logic, but at arbitrary indices TIDX and PIDX. With a star, either skip the X asterisk or consume one matching character and stay on the star. Without a star, both pointers advance. We store and return the result. Returning result allows _cache to memoize outcomes for these indices. We kick off the memoized recursion from indices 0. Now let's add an equivalent bottom-up DP that fills a table iteratively. DP 0, 0 answers the full string match question. We allocate a len text +1 by len pattern +1 table. DP, P, means text, T matches pattern P. The base case, empty versus empty, is true. This anchors the table. No text and no pattern always match. We fill the table backwards so that subproblems like dp t plus 1, p or dp p plus 2 are already computed. First match mirrors the recursive check. Iterating p from right to left lets us look ahead at p plus 1 safely. For a star, we either skip x asterisk or use a match and stay on JIDX. Without a star, both indices advance by 1. These transitions mirror the recursive choices, but in table form. The final answer is DP0, 0. Now let's add some quick tests to validate our implementation. This returns whether the entire text matches the entire pattern. First, A versus A should be false. Next, A versus A asterisk should be true because the star can repeat a. This case demonstrates how star repeats the preceding character. Finally, a versus that asterisk should be true, since dot star can match any sequence of characters. Dot star is a wild card for any sequence, so this final test returns true. Now we'll add the main Python file for the container with most water solution. Let's open the file and begin coding step by step. Let's start by adding quick complexity notes and importing lists for clear type annotations. The list type helps us annotate the input heights array, and the comments set expectations for performance. Now we'll define the solution class that LeetCode expects and note the two-pointer strategy we'll use. This class wrapper matches LeetCode's required interface for submitting solutions. Next, we'll add the method signature with type hints, plus a quick note about what the input represents. The method takes a list of integers and returns the maximum area as an integer. Initialize the running maximum and set 2 pointers at the extremes. We'll move them toward each other. Left starts at the first index, right at the last. This sets up the 2-pointer sweep. Create the main loop and compute the area as width times the limiting height, updating the maximum as we go. This update takes the best of the current maximum and the area formed by the two chosen lines. Move the pointer at the shorter line inward. Only a taller boundary can improve area when width shrinks. By advancing the shorter side, we give ourselves a chance to find a taller line and increase the area. Once the pointers meet, we've considered all candidates. Return the best area found. This returns the maximal area computed during the sweep. Finally, add a quick test to verify the implementation. For this input, the expected result is 49, which confirms our two-pointer logic works. Now we'll create the solution file for problem 0012. Let's open the file and start coding step by step. Let's start by documenting the complexity and noting that this solution needs no imports. Because the number of digits is bounded, both time and space are constant for this approach. Now we'll add the solution class container, as LeetCode expects the method to live here. Everything we build will be encapsulated in this class for LeetCode to call. Next, we define the method signature, taking an integer and returning its Roman numeral string. This method will decompose the number into thousands, hundreds, tens, and ones. We'll pre-compute mappings for the thousands and hundreds places to allow O1 lookups. Indexing this list by number / 1000 yields MM or MMM. Now we'll add the tens and ones tables, including subtractive forms like 4, 9, XL, and XC. These encode every possible digit for the ones place, including subtractive cases. We'll start assembling the answer by selecting the thousands and hundreds components using integer division and modulus. Number / 1000 isolates the thousands digit. Number % 1000 / 100 isolates the hundreds digit. Finally, we add the tens and ones components and close the parenthesis to return the complete string. Number percent 100 / 10 extracts the tens digit, and number percent 10 extracts the ones digit for direct table lookup. Let's add a quick test. For input 3, we expect the output 3. Run this to see the result. Change number to try more values like 58 or 1994. Now we'll add the solution file for problem 0013, Roman to integer. Let's open the file and start coding step by step. Let's start by adding the stated complexity comments and an optional typing import, which will let us annotate our values map. These comments document the intended time and space complexity for quick reference. Now we'll add the solution class. LeetCode calls methods on this class when running tests. Defining solution keeps our method in the standard LeetCode format. Next, we define the Roman2int method with a brief docstring describing its purpose. This method accepts the Roman numeral string s and returns the computed integer. We'll initialize an accumulator total, an index I to walk the string, and start a map of Roman symbols to their values. Total accumulates our answer, I tracks our current position, and values lets us look up symbol values quickly. Now we'll add the first few Roman numerals with their corresponding integer values. Each key is a Roman symbol, and each value is its base numeric value. Let's finish the mapping with the remaining symbols and close the dictionary. With this map complete, we can translate any single Roman character in constant time. Now we'll scan the string. If a smaller value comes before a larger one, it's a subtractive pair like 4 or cm, so we add the difference. This line handles subtractive notation by taking next minus current and adding it to total. After processing a subtractive pair, we skip 2 characters. Otherwise, we add the single symbol's value. Advancing by 2 ensures we don't double count the pair we just processed. For the non-subtractive case, we move 1 step forward, and when the loop ends, we return the accumulated total. This returns the final integer value after we've walked the entire string. Now we'll add a couple of quick tests. 3 should produce 3, and LVII should produce 58. Finally, test mixsiv, which uses several subtractive pairs and should yield 1994. Run the file to see outputs 3, 58, and 1994, confirming our logic for both additive and subtractive cases. Now we'll add the main Python file, where we'll build our step-by-step solution. Opening the file so we can start coding the tree-based approach. Let's start by noting complexity and importing list for type hints. This sets the context and keeps our signatures clear. The list import lets us annotate our function signature clearly for readability and tooling. Now we'll define a tree node. Each node stores its character, a map of children, and a flag to mark the end of a word. Children holds outgoing edges by character, enabling O1 navigation to the next node if a character exists. Next, we create the tree wrapper with a single root node. All words will be inserted from this root. The root acts as the entry point for every word, but it doesn't represent any character itself. Now we'll add an insert method. We start at the root and iterate each character of the word. This loop walks the tree character by character to build or follow the existing path for the word. If a character edge is missing, we create it, then advance. After processing all characters, we mark this path as a complete word. IsIn tells us the word ends here, which matters when a common path stops early at a complete word. Now we'll define the solution class and the method signature. It takes a list of strings and returns the longest common prefix. Type hints make it clear we take a list of strings and return a string. First, build a tree with all input words. This shared structure lets us traverse the common path efficiently. Inserting every string constructs overlapping paths that encode shared prefixes. Next, prepare to traverse. Prefix accumulates characters. Node tracks our current position starting at the root. Prefix will collect the common path characters as we walk down the tree. Now we'll walk straight down as long as there's exactly one child and we haven't entered a word. We append the only child character and continue. This condition ensures the path is common to all words. It must not branch and must not pass a word end. Finally, return the accumulated prefix. If no common path exists, prefix remains empty. This covers all cases: empty list, no common prefix, or shared prefix across all strings. Let's add a quick sanity check with two test cases, one with a non-empty prefix and one with none. Run these tests to see FL for the first set and an empty string for the second. Our tree walk stops exactly when branching or a word end occurs. Now we'll add our solution file, named 0015-3 sum.py. Let's open the file and start coding step by step. Let's start by noting the time and space complexity and importing list for type hints. We import list so we can clearly annotate arrays and return types. Now we'll define the solution class and a helper toSumII. We set two pointers, one just after I and one at the end. These two pointers let us scan inward to find pairs that complete nums, I, to sum to 0. Inside the loop, we compute the current triple's sum. If it's too small, we move left-rightward. If too large, we move right-leftward. This sum drives our two-pointer adjustments and keeps the search O, N, for each fixed I. When the sum is exactly 0, we record the triplet and move both pointers to look for the next candidate. Appending here captures one valid triplet before we continue searching. To avoid duplicate triplets, we skip over repeated values on the left pointer after a match. This check prevents adding the same triplet multiple times. Next, we'll implement 3-sum. We sort first to enable the two-pointer strategy and make duplicate handling predictable, then prepare the result list. Sorting is crucial for two-pointer traversal and duplicate skipping logic. We iterate over each value as the first element. If it's positive, we can stop early. Otherwise, we skip duplicates and call our helper to find pairs. This condition ensures each distinct first value is processed exactly once. Finally, we return the list of unique triplets that sum to 0. Our algorithm is complete. Sort, iterate distinct anchors, and use 2 pointers to collect results. Let's try the classic example with negatives and positives to see valid triplets. We call 3sum on the input and print the result to verify correctness. Now a case with no valid triplets, and a duplicate-heavy case of all zeros which should yield a single triplet 0, 0, 0. These tests demonstrate both no solution handling and deduplication, producing a single unique triplet.